So in part 2, we're going to finally start solving or finding all the zeros. So example 3 says find the complex zeros of the polynomial function f of x equals x to the third plus 13x squared plus 57x plus 85. So we're going to use the same steps here we did in the previous section, section 5.6. We're simply not going to stop when we hit those imaginary zeros. So we're going to continue on and find all of the zeros. So let's first recognize that we're looking for 3 zeros, and when we are finished, we will find all 3 zeros. We now need the list of P over Q. That's the possible rational numbers. Again, rational numbers meaning the numbers that you could are either integers or decimals or fractions that are repeating or terminating. So for us, that's plus or minus. Remember, P are all factors of 85. Factors of 85 are 1, 5, 17, and 85. Over all factors of Q, and Q in this case is a 1. So our list is just literally 1, 5, 17, 85. Not a very big list. That's going to be nice. Okay, we're then going to look at the graph. And what we're going to notice on the graph is when you graph this thing, it crosses over here at -5 and it doesn't cross again. So it tells us some pretty important information. It tells us, first of all, that there's only one real zero over there at -5. The other 2 zeros have to involve I. So we're going to go through the synthetic division process with the -5 and see what happens. So -5. And then we're going to have our 1, our 13, 57, and 85. We'll bring down the 1, multiplying, remember, -5. Adding that column is going to give us 8. Multiplying gives me -40. Adding that column gives me 17. And 17 times the -5 is 85, which gives us 0. So sure enough, it worked. This is our proof down here. Yes, indeed, that is 0. Well, what's left in terms of the 1, the 8, and the 7? Well, this is a 1x squared plus 8x plus 17. So now we need to factor that guy. So x squared plus 8x plus 17. We're going to set that equal to 0. Well, unfortunately, there are no factors of 17 that are going to add to 8. So we're going to use the quadratic formula and go solve it that way. And we already know that when we do this, we're going to end up with a negative underneath the radical because we know that the other 2 zeros involve I. They are imaginary solutions. So we got to go find them. -8, that's the opposite of b, plus or minus the square root of b squared, which would be 64, minus 4 times 1 times 17, all over 2 times 1. So that would be a -8 plus or minus the square root of 64 minus 68, all over 2. So that's a -8 plus or minus the square root of -4 over 2. And the square root of that -4 is going to be a -8 plus or minus 2i over 2. And finally, we can divide out the 2's. That's going to give us -4 plus or minus. Woo, there we are. Okay, so what do we got? Well, we now know that the zeros of this polynomial function, the complex zeros of this polynomial function, are the -5, the -4 plus I, and -4 minus I. And they all are. It does ask us to write it in factored form. So we've now solved that and found it 0. In factored form, we're going to take each of those and put them back with a factor. And I've kind of run out of room. So good thing you guys can pause and copy stuff. I'm going to write it right up here. So in factored form, f of x would factor into. So each of these I'm going to write as linear factors. That would be x plus 5. That's the -5. Now, as I bring these guys over, remember to switch both of the signs. So you'll have an x plus 4 minus I. And then we'll have an x plus 4 plus I. You know, when you look at this, you should see those conjugate pairs. So here's the -I, here's the positive I. Notice the sign on the 4 is the same because the pairing only happens on the i's. And there it is. We found the zeros and we factored the polynomial function. So, yay! Okay, let's try a 4th degree polynomial. So let's wrap it up 1 more degree. See what that does to our process. So this is example 4. Our polynomial function is f of x is equal to 3x to the fourth plus 5x to the third plus 25x squared plus 45x minus 18. That's a 3 sitting there. It doesn't look good, but it's a 3. Hey, there it is. So we now know, because it's a 4th degree polynomial, that we're looking for 4 zeros. Our P over Q list is going to be a little more complicated this time. So factors of 18 are 1, 2, 3, 6, 9, and 18. But we have a Q of 3, so that's going to be over 1 over 3. So our list becomes a 1, a 1/3, 2, 2/3, 6 over 1. 6 over 3 is 2, it's already listed. 9 over 1. 9 over 3 is already listed, and 18 over 1. So it's a more extensive list. And again, before we had graphing calculators, what we would do is actually literally try all of these numbers until we found one that gave us a 0 as a remainder. There are a couple other theorems that we didn't do that gives us a little bit more guideline, but it was basically trial and error. So luckily for us, we get a graphic. So the next step would be to graph it. And from the graph, what we're going to notice is it crosses the x-axis twice. That tells us it has 2 real zeros. That means the other 2 have to be complex zeros. And so from the graph, we're going to try -2. So the graph, we're going to say x equals -2. So my coefficients this time are 3, 5, 25, 45, and -18. We'll bring down our 3, multiplying is -6, -1. Because we, whoops, +2, be really careful, 27. 27 times 2 is a -54. That's going to give me -9. Multiplying gives me +18, which gives me -0, which we expect. So, yay. Okay, now we need to pull the other 0 that's a real 0 off that graph. And if you do, you'll notice that it occurs somewhere between 0 and 1. So I take a look at my fractions, and it looks like it's closer to 0 than it is to 1. So we're going to use the 1/3. If 1/3 doesn't work, we'll go try the 2/3. But let's try the 1/3 because it looks to me like it's a 1/3 on the picture. So 1/3. And hopefully you graph that either using decimals or your calculator. 3 times 1/3 gives me 1. That's adding gives me 0. 0 times 1/3 is 0. Adding is 27. And 1/3 of 27, sure enough, is 9. Adding is 0. Woohoo, and there it is. Okay, we started off with an x to the 4th. When we went through and did synthetic division one time, the depressed equation was an x cubed. Doing the synthetic division the second time gives me an x squared. It's my depressed equation. So this is 3x squared plus 27. Well, we can solve that. So now we're going to let 3x squared plus 27 equal to 0. We don't need the quadratic formula this time. There's a quicker way to do this. We're just going to move the 27. Then we're going to divide out the 3. So x squared is equal to 9. Whoops, -27 and -9. And x is equal to plus or minus 3, the square root of -9. So that worked out really nice. So our zeros of the polynomial are the -2, the 1/3, the 3i, and a -3i. They also want us to write it in factored form. I need to be a little careful. So in factored form, I would have f of x is equal to, and again, I'm just taking these guys and putting them back as our linear factors. From the -2, that translates as an x plus 2. The 1/3 would come over as an x minus 1/3. We would then have an x minus 3i and an x plus 3i. A little too ambitious in my arrow there. So x minus 3i and x plus 3i. And if you boil this all back out, you're going to end up right back up here. I would like to clean it up because it's going to drive me crazy. Sorry. When you multiply this x times this x times this x times this x, you're not going to get that 3 out front. You're just going to get an x to the 4th. So where's that 3 coming from? It's tied in this one right here. So let's rewrite that as x plus 2 times 3x minus 1 times x minus 3i times x plus 3i. And that works better for us. Another way of thinking about this is, remember this 3 that we divided out back over here? It's actually sitting right here. It doesn't affect zeros, but it does affect the stretching, which is what the 3 out in front is a measure of, is that stretching in the vertical direction. So if I take that 3 and distribute it back into this factor alone, then that would give me my 3x, and that's going to give me my 1. So that's another way to think about it. But there it is. I think that's a much friendlier form of it. And here are our zeros.